Okay, a Ferris wheel pulls 0.15 Gs. What G force do they feel at the top and the bottom? Okay, first let me explain what pulling 0.15 Gs means. That means that if we figure out the acceleration, right, the centripetal acceleration, maybe we use 4 pi squared r over t squared, right, or maybe we use v squared over r, but whatever it is, we figure it out, then we divide by 9.81, and that equals 0.15. Okay. Now, this, by the way, this acceleration in meters per second, this is G's, right? In meters per second squared, that would be 1.4715. If you take, that's meters per second squared, right? If you take that and divide by 9.81, you get 0.15 G's. Okay, so that's what that means. Okay. Now, to figure out what G force you measure or feel at the top and the bottom, okay, we're going to use a very sophisticated concept, and this is the principle of equivalence, and that is that accelerations and gravitational fields are equivalent. Okay, so understand that we've got a gravitational field, and the gravitational field is 1g is what we feel, right? Okay, so right here we're going to feel 1g. Oh, I'm sorry. If we're not accelerating at all, we're going to feel 1g, right? In general, you always feel 1g plus whatever the ride is doing. Okay, so let's say the ride is accelerating up at 2 Gs, you'll feel 3 Gs. If the ride's accelerating at 1/2 of a G, you'll feel 1.5 Gs. If it's not accelerating at all up and down, you'll feel 1 G. Okay, if it's accelerating up at 5 Gs, right, like the Saturn V rocket, you'll feel 6 Gs. Okay? Okay, what if I'm accelerating down? If the ride accelerates down at 1/2 a G, well, down is negative, right? So it'll be 1 G plus negative 0.5 of a G, right? That'd be, I'd only weigh 1/2 a G, right? So the thing to understand is that this ride at the top, we're accelerating down. If we go in a circle, and at the bottom, we're accelerating up, okay? So at the top, let's figure this out, right? It's 1 G plus whatever the ride is doing, right? Wow, I can't spell ride, okay? At the top, it would be down 0.15. Well, down 0.15 is just negative 0.15. At the bottom, it's positive 0.15, yes? Okay, so I just go 1G plus negative 0.15, and I get 0.85. That's what you feel at the top. That's G's, right? At the top. And then at the bottom, it's positive 0.15, so I go 1G plus a positive 0.15. Okay? Is equal to 1.15 G's at the bottom. So at the bottom, you feel a little heavier, and at the top, you feel lighter. And the cool thing is that if they're a big enough Ferris wheel, there's no experiment you could do to tell the difference between gravity changing, right, or just being on a ride that changes the gravity by accelerating. That's the principle of equivalence. Okay. Now, I'm going to show you a startling slide here. Let's just keep going here. This is the actual G-force on the Ferris wheel, right? So here we're heavier, right? This is the acceleration, right? This is actual meters per second squared. We took a G-force meter on there, right? This is where I'm heavier. So this is actually when I'm at the bottom. If you look at this thing, right? Remember, you're at the bottom, it's 1.15 Gs. At the top, it's 0.85 Gs, right? In the hypothetical example, these numbers don't match that, okay? But notice that where it's heavier, this must be when we're at the bottom. And where it's lighter like this must be where we're at the top. And you could actually look at the period of it's like something like 24 seconds, and you can calculate that. We know the radius. We can do all kinds of magical calculations with this thing. Okay, but just when you look at these G-force things, right? This is when we're at the bottom, when the G-force adds on to gravity. Here at the top, it subtracts from gravity.